Okay? So this is for today. Today we will deal with a few topics. The first one is the inverse problem. Okay? We're given an impulse response. If we are given an impulse response, h of m, okay, which has a finite length of n plus 1, okay, from h0 to hm, an nth order FIR system. Okay? We're given an impulse response. How do we find the lattice implementation? That's a question. And that's a problem we are going to discuss. Okay? That's the opposite direction, right? So last time on Tuesday we talked about given the lattice all the coefficients, then how do we calculate the impulse response? But now today we talk about the opposite. Okay? Given the impulse response, can we find the lattice implementation for that desired response? The desired response. We might have design using pipeline type 2, using window, and using optimal filter or whatever. Okay? So how do we find is there a systematic way to find to implement your desired filter in the lattice form? That's the question. So given any FIR, how to implement in the lattice form. In the lattice form. Okay? So that's the first half of today. So in doing that, we will essentially be undoing, because this is the opposite problem. Okay? So I will guide you through a kind of my way of visualizing what is exactly is going on in algorithm 2. So once you are able to visualize the entire algorithm, you can kind of in your mind reverse every step. Kind of reverse every step, and that'll be our answer to the first topic. Okay. Any comments so far? Any questions? So it's the opposite problem. Okay. It's an opposite problem, and I suggest essentially we are going to be undoing things, undone, right? Undo to be undone. All this argument is going to be undone. That's my strategy. Okay. So this is about undoing. Friend and friend, like and like, do and do. Algorithm and algorithm. Okay. So that's my suggestion. The first topic we're going to cover. And the second topic we are going to cover is some properties. Okay, let me just say we're going to study the inverse system. The inverse system to a lattice FIR. So the lattice FIR goes, the flow, the information flow goes from left to right. Okay? And we go to. So that's our lattice, the FR. But the inverse system, so it turns out, let me just review the conclusion. It turns out that if all the lattice coefficients in this K1, K2, okay, if all the lattice coefficients have an absolute value of less than 1, then it's very nice. Then this system is invertible. Or another way to say it is then this system is a minimum phase system. Okay, let me just write it down. It turns out that if all the lattice coefficients have an absolute value of less than 1, it turned out that this system H of Z is minimum phase. And we know that the minimum phase system can be inverted in a stable manner, right? So if that happens, it turns out that we have the system is invertible. Is invertible. Invertible. And we'll be looking at the inverse system, also a lattice structure, but now that inverse system has information flowing from right to left, and there's a feedback. Now it's generally an all-pole, it's an IIR system. FR, the inverse of the FR is always an IIR. Okay, so we'll talk about that. The inverse system actually involves IIR with feedback, but similarly with the lattice structure. And I'll show you too. Okay? So mainly these are the two topics for today. All right? Any questions? Okay, so let's talk about the first topic first. This is about doing the algorithm number 2. So let's just, from now I invite you to kind of give a mental picture of what's going on. Okay? Sometimes you write a computer program. You must have a mental picture somewhere in your mind, data structure, right? So this is similar. So algorithm number 2, so let's talk about if we are given all the lattice coefficients, k1 to kn. These are given. And last time we said that, I'll just write it down again. So this is exactly the same thing from last time. There is a double loop in here. For I from 1 to n, the inner loop is, let's say, if I is greater than 1. If I is greater than 1, then we have another 4. Then for j from 1 to I minus 1, we are going to define this actually an array or a vector, if you will. Okay? So this is an alpha array. So maybe let's just define. Okay, let's define this alpha array. Take 都放 alpha 出体式. Let's define an alpha array. This will become more convenient. Let's define an alpha array to be 1 minus alpha. Actually, I should put an index I here. Okay. Minus I1 and minus alpha I superscript I2 and so on, and all the way to minus alpha superscript I subscript I. So this is, by MATLAB notation, this is an array. Okay? Let's just in our mind create an array. An array that actually the length is going to be growing. Okay? Let's think of an array. Okay? An array of length I equals 1. Right? Any questions so far? And please don't worry about the minus sign here because it's just a matter of definition. Please don't worry about the minus sign first. But now, it turns out that the algorithm just gives us clearly how to fill the array. How to fill the array. Okay? So because we are being consistent with our notation from last time. So here, inside the double loop, we have this expression. For every I and j, we are going to calculate a superscript I and subscript j, aij, based on results from last round. So I equals 1 is first round, I equals to second round, and so on and so forth. Okay. So let's just refer to I as the round number. Round 1, round 2, round 3. Okay. So inside here, of course, we'll close this for with an n. But inside this closed for loop, there is only one line, which tells us how to calculate the alpha values for the current round, the ith round, based on the result from the I minus 1 round, based on the result from the previous round. Okay, so that's the idea. So we know that I minus 1 here, and sub j. For every j, we're going to do the same thing. And minus ki. I is the k, where k is just drawing from here. K is given. Okay? Ki. And alpha I minus 1, here we have I minus j because of time reversal property. So this is the contribution from the bottom line. This is a contribution from the top line, direct feeding. Is that clear? Is that making sense to you so far? I'm saying that so this first term here comes from here. And really, this second term here comes from right here, with the minus k I. Okay, and they're merging on the top lane somewhere here, exactly after the ith unit. So really, this equation corresponds to the structure very well. And we are using the time reversal property because we know something from bottom has a time, we already has a time reversal embedded. Okay, we assume that time reversal really is true, and we have proven. So in any question on how to read this line? How do we read this line? So this algorithm is really corresponds to the structure very well, and it also uses the time reversal property. Okay, so far so good. Anyway, so this is just from last time. So n, right? So n from j to I minus 1. But now after we run j from 1 to I minus 1, we haven't figured out aii, right? This is ai1, ai2, all the way to ai minus 1. So we're missing aii, right? So last term is missing. So it turns out the last term is just simply ki, simply ki. And then we close the first loop with an n. So that's the algorithm. And it turns out that if you trust me, if you trust the textbook, it turns out that after running the double loop, so we increase I. So at first I equals to 1, and then I equals to 2. And we'll be calculating alpha superscript 2 of 1, 1, 2. Based on the previous one, and we repeat this process. We calculate the third round based on the result of the second round. Okay? Rather simple algorithm. After a few loops, it becomes easier, right? After a few loops, I hope it becomes it's making more sense than last time, right? So let me put a kind of a comment, okay? After all, when we just finish the double loop, what we'll get is actually that we'll get this vector. And it turns out that, let me just put my comment to the right, because it's too low here. But it turns out that after running the loop, the double loop, after running a double loop, we'll be able to fill we get alpha m. We'll get an array of length m plus 1 with leading coefficient 1, but otherwise the second term is alpha m 1, all the way to alpha m, or maybe with a minus sign, it's not super important. Okay? But after running completing this double loop, we will get an array, right? And this array, how does it relate to the impulse response we want to calculate? And the result is quite simple. So let me just share with you. And it turns out that this A, it turns out that, let me say the impulse response, H of Z, will be exactly 1 minus summation alpha m j v to the minus j. And of course, you don't know here j is not j. J is an integer. Okay? J is an integer. Where j goes from 1 to n. Okay? So I'm just confirming with you, to reassure with you that this algorithm, after you complete running the algorithm, the result is the impulse response. The impulse response is completely determined, given all the lattice coefficients. Okay, so with this picture in your mind, so So after every round, you have an array. And the length of the array is growing. Can you agree on that? After every round, we have an array, and the length of the array is growing. Is growing. So exactly what's happening is here. So another way to look at that equation over there is that I'm going to propose that suppose that after the I minus 1th round, after I minus 1th round, what you get is alpha 1 to alpha of I minus 1. I'm omitting the superscript, okay? Here I'm omitting the superscript because I already said this after the result. The temporary result immediately after I minus 1th round. Okay, so here allow me to omit the superscript. Allow me to omit the superscript. But what we get is that you always get a result like that, right? After any given round. But for the next round, this algorithm is suggesting that you first simply reverse it in reverse the order, copy everything but in reverse order. Okay? Copy everything but in reverse order. And then you are going to multiply this second array by ki. You're going to multiply this second array by ki. And then you are going to sum the result. You're going to sum the result, and the result has a length of still I minus 1. Okay? Something. And it turns out that the result would be the next round. What you need for the next round. The result will be what you need for the next round. Except that the final term hasn't been determined. Okay? Except the final term. So here I'm visualizing the algorithm. First, you do the time reversal. Second step, you multiply by k. A third step, you just add the two arrays. This is basically a linear combination, right? Linear combination of two vectors, if you will. And then the length remains to be I minus 1. You need one more term. And that one more term is exactly, you just append the array. Let the length of the array grow. You just append the array and increase its length by 1 by appending one more item, one more element that is exactly ki. Appending. This is an action of appending something. Okay? So that's exactly the algorithm. It's very simple. You probably all the way to initial line, you have the probably length 1 array number. Okay, we just use the number 1, and then just keep growing. Okay, keep time reversal, multiply by k, linear combination, and append the last item. 4 steps, very clear. Can we all visualize this? This is what I want to suggest to you. Yeah, I'll pause a little bit. Okay, 4 steps. The previous result, which is time reversal, multiplying by k, and then do a linear combination, and then append an extra item. Okay, can we all agree that this is, okay, you have that in your mind, right? I want you to have this in your mind. So once you get this, the next thing is becoming very simple. Next, I'm going to invite all of you to work together. Then how do we undo the algorithm? How do we undo the algorithm? Because seriously, if you can undo the algorithm, then given a input stuff, you can backtrack and figure out what are the lattice coefficients, k1, k2, all the way to kn. Right? Is that making sense to you so far? If you can picture this algorithm, you can visualize this algorithm, then I bet you'll be able to undo it. Want to try? Any suggestions? Are we ready? Are we ready to undo the algorithm? So to undo officially, we start with the result. Okay, we start with the complete result. That's basically 1, and minus alpha 1. And here again, let me omit the superscript because we are just initializing with minus alpha 2 and minus alpha n. So the entire length of this array is n plus 1. All right, so we are given this, and we know that this is exactly the impulse response. In fact, this is the way MATLAB would ask you to encode an impulse response. That's the MATLAB convention. This is exactly the MATLAB convention, if you are familiar with that. Okay? So anyway, it's an array representation of your filter. And you have n plus 1 coefficients. And this defines exactly the impulse response. Okay? Now, if we are given the impulse response, so this is if we are given the impulse response, how do we backtrack? How do we backtrack and eventually figure out all the k coefficients? Any suggestion? What's the first step? How do we undo this algorithm, which consists of 4 steps for each round? So which one should we undo first? Remove this last one, right? Because it's being appended to the end in the final moment, right? So suggestion, so let's try. Try first. Okay, I'm just going to draw a picture. First is just to remove this. I will say Kn is exactly minus alpha n. There might be a plus sign, I'm not sure. So that's kind of the first step. I agree with it. The first step is to remove this thing here. Okay? So now we are back to here. Now the length. After the removal of the last item, now we are back to an array with n minus 1 items. With n minus 1 items, and then how do we undo linear combination? Well, how do we undo linear combination? How do we undo linear combination? Or should I say, how many variables do we have and how many equations do we have? Do we have a unique solution? Okay, that's the case. Okay, we have. This is known. Okay, so to undo linear combination, we know that a k m is given, right? K given, and we have to figure out 2 vectors which linearly combines to our given vector. Can we do that? Is there a unique solution? That's the question. Can we undo this linear combination? And it turned out we can. So let's write it in more detail. Okay? So here we have alpha 1 plus ki times alpha I should be n minus 1 equals to this thing here is alpha with a superscript n of 1. And we have alpha 2 times ki alpha of n minus 2 is alpha with a superscript n, then the number 2, and so on. And finally, we have alpha n minus 1 plus ki alpha 1. Because these are, remember that these vectors, we assume we are using the time reversal property range. But we are assuming that these 2 vectors are exactly in time reversal. That's why we have now alpha n plus, and we have the final equation that gives us this, superscript n, n minus 1. So exactly here, we have n minus 1 equations. N minus 1 equations with n minus 1 variables. All right? So, unless you are super unlucky in the algebra, usually, let me wave my hand. Usually it has a unique solution. Okay. Very likely we have a unique solution. I'm not checking the determinant or anything. But anyway, so probably we indeed have a unique solution. Okay? unique solution of alpha 1. Now we are reducing our order from n to n minus 1. Probably we have a unique solution for that. Okay, sorry for repeating about it. Right, so we are good. Actually, we are good. We have undone the linear combination, and that reduces our order by 1. Okay, so that's exactly the reverse algorithm you picture. Okay, this is my picture I want to share with you. How do we undo the lattice scattering process? Okay, now so that when we are given the input response, we can just by undoing the algorithm n times, eventually we figure out all the k coefficients. And so so after undoing the linear combination, again we know that the last item is the next lattice coefficients. So this is now our new input to the second round. So now we have successfully removed 2 of them. And the length of the vector further shrinks. And we just keep repeating until we figure out all the lattice coefficients. It's always going to be that last element which we can remove, which we can get rid of. Okay? Okay, so we will be seeing a few examples. Okay, we'll be seeing a few examples. That's essentially the algorithm. Okay, so this is actually, if you just look further, these 2 equations actually tells you how to figure out alpha 1, subsequent, and alpha, the first and the last element for the next round. Okay, so actually it's like the second to the last equation help you solve the second variable and the second to the last variable. So it has to be some basic structure in there. Okay. Otherwise, this is just a way to undo the algorithm by undoing the algorithm. Okay. Any questions? Is there anything that is not clear? We have time. I don't think this way of explanation is in the textbook. Okay, this is my sharing. This is the way I look at this reverse algorithm. Okay, so just to conclude, to summarize, now finally we can say that if we are given the impulse response, we can use the reverse algorithm, inverse algorithm to implement it using the lattice structure. And the other way around is easier. Okay? The other way around is just given the lattice structure, given all the lattice coefficients, of course we can calculate the impulse response. Right? And next, I would like to share with you a few properties that I just discovered this morning. When I was preparing for this lecture, I checked the internet. I found somebody in Russia. Somebody in Russia had some nice comments about lattice structure I would like to share with you. Okay, I just barely know a little bit more before you do. So now I'm going to share with you. But that Russian person, something. Thanks to somebody in Russia. Okay, so that person said, yeah, when we have a lattice structure, we have one input and two outputs. And he just boldly called the top lane the result, the outcome, and you know that assume that all the delay is at the bottom. Okay, all the delay is at the bottom. He just boldly called the output on top. He calls it, he or she, the person calls it the minimum phase output. Okay, so this y of n is x of n is the input, and on the very right on top, he calls the output the minimum. He refers to this as a minimum phase output. And surprisingly, the output at the bottom line, this y prime also has an n. You want to give a guess? If top is minimum phase, what is bottom? O pass. Why? Minimum phase O pass decomposition. Right? Wrong. Okay. The bottom is called maximum phase output. So I thought this is awesome. I'd like to share with you. So I pondered. I thought about it. Is he joking? Is he kidding? Are you kidding or not? Minimum phase, maximum phase. And then I thought I can agree with him. But this is my comment. Okay. I think what he meant is that if all the coefficients here have absolute value of less than 1, okay? I think what he meant really is as this necessary condition. Okay? This output is going to be, the relation between output and input is minimum phase 1. This filter is a minimum phase filter if all the coefficients, all the lattice coefficients there have an absolute value of less than 1. Okay? But then how do you kind of prove that? What's the reason behind this? What's the kind of reason behind? That needs some explanation. So here, I'd like to share with you quickly the inverse system. Okay? Here we have an FIR system. Now I'm going to share with you if all the coefficients here are minus k1, still the same notation. Same naming, same notation. Then the inverse system also have two lines. But the bottom line is going from right to left. Right? Top line is going left to right still. And we have crossover. And the crossover now is pointing backward. The crossing over is pointing backward. Pointing backward. Pointing backward. And this is the structure of the inverse system, turns out. So we still have the input here. Let's say if the input is y of n. So we're imagining that we are concatenating this system to a forward system. Okay? So if the input here is y of n, and then blah blah blah, same thing. And then in the very end, still we have crossing over pointing backward. The crossover branches pointing all points backward. And again, we are going to assume that the delay block is at the bottom of that node. The inverse right here. The inverse right there. Okay, and so on and so forth. And the inverse right here. And if we close the final branch like that, branching, going backward and to the left, then in this place we are pulling an output. Let's just call it W of n. Okay, W of n. Whereas actually here we have another output pointing to the left, going to the left. And this we call it V of n. Okay? Y, W, and V. And it turns out that if all the coefficients, okay, by the way, we also need to define the coefficients carefully. Let's say this branch is associated with the coefficient Kn. And this one going downward is minus of Kn. And similarly, K of n minus 1, minus of Kn minus 1. So you're super careful about the order and the sign. And it turns out that this system, we consider a relation between y and w. Okay? And note that it has a lot of feedback. There are actually feedback loops. For example, this is a feedback loop. Right? And for example, this is also a feedback loop. So there are a lot of feedback loops. This looks very complicated. But let me assure you, without showing you the derivation, it turns out that if we put y back into this system, it turns out that w of n is exactly, we can recover s of n. Again, if all the scattering coefficients, all the lattice coefficients have absolute value less than 1. Okay? And also, to show you, to end today's lecture, the top line here is called the all-pole output. And it turns out that this thing here is called the all-pass output. Very strange, right? This thing here is called the all-pass output. And exactly why we should call this all-pass, I'll discuss. Let's discuss next week what we need. Okay? So anyway, so this V and N is called the all-pass output. And this is something I learned from the web, from the internet, from somebody in Russia. Okay, I will share with you. Have a nice weekend. See you next week. See you. Thank you.